All right, let's dive right into this explainer. Today, we're going on a seriously fascinating evolutionary journey of propulsion. We're going all the way from the mechanical gas guzzlers of 1876 straight through to the high-tech, computer-controlled hybrids sitting in your driveway right now. It's a story of thermodynamics, ingenious engineering hacks, and honestly, the relentless pursuit of squeezing every absolute last drop of usable energy out of our machines. Our roadmap for today is pretty straightforward. 1. The baseline Otto cycle. 2. Spark versus compression. 3. Hacking the combustion cycle. 4. The electric motor shift. And finally, 5. The ultimate hybrid powertrain.
Starting things off with Section 1, the baseline Otto cycle.
So back in 1876, a guy named Nicholas Otto essentially wrote the rulebook for the automotive game, and it lasted for over a century. The really crucial point here is understanding his 4 basic steps. First, the intake stroke draws in a mixture of fuel and air. Second, the piston rises to compress that mixture. Third, a spark ignites the fuel rapidly, forcing the piston down in the power stroke. And fourth, the exhaust valve opens to push all those leftover gases out. Now, operating under strict physical limits, this standard Otto cycle typically yields only 25 to 40% peak thermal efficiency. To put that into perspective, that means the vast majority of the energy in your gasoline is literally just lost as waste heat.
Moving right along to Section 2, Spark versus Compression.
You see, gasoline and diesel engines play this combustion game very differently. Gasoline engines compress a volatile air-fuel mixture at a ratio of about 8 to 1 up to maybe 12 to 1, and then they use a spark to ignite it. If you compress it any more than that, the fuel might detonate prematurely, which is a highly damaging effect known as knocking. Diesel engines, however, they only compress pure air. Because there's no fuel in the cylinder yet, they can squeeze that air at massive ratios, anywhere from 14 to 1 all the way up to 25 to 1. When diesel fuel is finally injected into that superheated, highly pressurized environment, it spontaneously ignites. This extreme pressure makes diesels inherently more thermally efficient. In fact, massive marine diesels can hit a staggering 51.7% efficiency. Plus, their robust build gives you that massive low-speed torque they're known for.
But, efficiency isn't the whole story. We absolutely have to look at the environmental trade-offs objectively. Gasoline engines burn a homogeneous mixture, meaning they emit fewer particulates. But their lower efficiency means they pump out more total carbon dioxide. They rely on three-way catalytic converters to clean up their act. Diesel engines, on the other hand, get 20 to 30% better fuel economy, which translates to lower CO2. However, that high-temperature pressurized combustion creates a lot more nitrogen oxides, or NOx, and fine particulate soot. So to meet strict emissions regulations, diesels rely on heavily advanced, complex after-treatment systems, like particulate filters and selective catalytic reduction systems.
Which brings us to Section 3, Hacking the Combustion Cycle. If traditional engines are boxed in by these strict thermodynamic realities, how do we improve them? Well, engineers realized they could legally hack the standard 4-stroke process by developing what are called overexpanded cycles. The goal here is basically to make the expansion, or power stroke, functionally longer than the compression stroke. Think of it as putting the engine on the Atkinson diet. By keeping the intake valve open for the first 20 to 30% of the upward compression stroke, the engine pushes a little bit of the air right back out into the manifold. This drastically reduces the physical work the engine has to do to compress the air. But once combustion happens, the piston still gets its full long travel downward, extracting maximum mechanical work from those expanding gases. It's brilliant.
The original concept for this is the Atkinson cycle. And while it definitely maximizes your fuel economy and thermal efficiency, it comes at a cost. It suffers from extremely low power density at lower speeds. Basically, it lacks low-end pep because, well, you're bleeding off some of your air. The Miller cycle hacks this system even further. It uses that exact same delayed valve timing, but adds forced induction, like a supercharger, to cram more air back into the cylinder. This perfectly compensates for the power loss while keeping all those sweet efficiency gains.
Next up, Section 4, the electric motor shift.
Even with all those brilliant combustion hacks, internal combustion just has a physical ceiling. Electric vehicle traction motors flip the script entirely. Let's start with AC induction motors. Here, alternating current creates a rotating magnetic field in the outer stationary part called the stator. But here's the fascinating part. To get the inner rotor to spin, it has to spin slightly slower than the magnetic field around it. This difference in speed is called slip, and it induces the magnetic field in the rotor to create torque. Because they rely entirely on this induced field, they completely avoid the need for rare earth metals. This makes them incredibly durable and cost-effective, while still hitting a highly impressive 90 to 93% peak efficiency.
But if we're talking about absolute peak performance, we have to look at permanent magnet synchronous motors, or PMSMs. Instead of relying on slip to induce a magnetic field, PMSMs physically embed highly powerful rare earth magnets right into the rotor itself. Now, this does mean relying on complex and sometimes volatile rare earth supply chains, but thermodynamically, it means zero slip. The rotor locks into perfect synchronization with the stator's magnetic field. This allows for incredibly precise speed control and completely eliminates the heat energy that gets lost in a standard induction motor. And the result of that perfect synchronization? A staggering 95 to 97% peak efficiency. Let that sink in for a second. Compare that to the 25 to 40% efficiency of the traditional gas engines we started with. It is a monumental, physics-defying leap completely beyond the limitations of fossil fuels.
Finally, Section 5, the ultimate hybrid powertrain.
The crucial point to take away from all of this is that modern automotive engineering doesn't force us to choose just one of these technologies. Every single powertrain has a highly specific, optimal application based on its unique mechanics. Spark ignition is lightweight and cheap, perfect for everyday commuting. Diesel's heavy-duty torque rules commercial freight. The rugged AC induction motor is absolutely perfect for utility vehicles and secondary all-wheel drive axles. And the ultra-efficient permanent magnet motor, that's the reigning champion for high-performance and long-range EVs.
But what if you synthesize them? By pairing a highly efficient, modified Atkinson cycle combustion engine with a torquey, permanent magnet electric motor, you create an absolute masterpiece of practical engineering. Remember how we said the Atkinson cycle lacks low-speed power? Well, an electric motor produces its maximum torque at 0 RPM, so the electric motor easily handles the heavy lifting of accelerating you from a stoplight. Then, once you're up to cruising speed on the highway, the system transitions over to the Atkinson engine, operating perfectly within its narrow, highly efficient sweet spot. Your daily commute gets incredible gas mileage, because this hybrid system brilliantly masks the individual weaknesses of both engines, while perfectly highlighting their strengths.
Which leaves us with a really fascinating final thought to consider the next time you get behind the wheel. We've taken Nicholas Otto's 1876 invention, hacked it with Atkinson valve timing, and seamlessly blended it with 21st century rare earth electromagnets. So the question is, are we finally nearing the absolute thermodynamic limit of vehicular propulsion? Or, given the sheer ingenuity we've explored today, is there another major engineering hack waiting just under the hood? Thanks so much for joining me on this explainer, and keep your curiosity revved up.